Erythro redirects here. For the fictional planet, see Erythro. Diastereomers are a type of a stereoisomer. Diastereomerism occurs when two or more stereoisomers of a compound have different configurations at one or more of the equivalent stereocenters and are not mirror images of each other. When two diastereoisomers differ from each other at only one stereocenter, they are epimers. Each stereocenter gives rise to two different configurations and thus increases the number of stereoisomers by a factor of 2. Diastereomers differ from enantiomers in that the latter are pairs of stereoisomers that differ in all stereocenters and are therefore mirror images of one another. Enantiomers of a compound with more than one stereocenter are also diastereomers of the other stereoisomers of that compound that are not their mirror image. Diastereomers have different physical properties and different chemical reactivity. Diastereoselectivity is the preference for the formation of one or more than one diastereomer over the other in an organic reaction. Syn/anti, when the single bond between the two centers is free to rotate, psi-trans descriptors are invalid. Two widely accepted prefixes used to distinguish diastereomers on spar-cubed hybridized bonds in an open-chain molecule are syn and anti. Mazamune proposed the descriptors which work even if the groups are not on adjacent carbons. It also works regardless of CIP priorities. Syn describes groups on the SAME face while anti describes groups on opposite faces. The concept applies only to the zigzag projection. The descriptors only describe relative stereochemistry rather than absolute stereochemistry. Erythro/threo, two older prefixes still commonly used to distinguish diastereomers are threo and erythro. In the case of carbohydrates, when drawn in the Fischer projection, the erythroisomer has two identical substituents on the same side and the stereoisomer has them on opposite sides. When drawn as a zigzag chain, the erythroisomer has two identical substituents on different sides of the plane. The names are derived from the diastereomeric aldoses erythros and threos. These prefixes are not recommended for use outside of the realm of carbohydrates because their definitions can lead to conflicting interpretations. Another threo compound is threonine, one of the essential amino acids. The erythro diastereomer is called allothreonine. Multiple stereocenters. If a molecule contains two asymmetric carbons, there are up to 4 possible configurations, and they cannot all be non-superimposable mirror images of each other. The possibilities continue to multiply as there are more asymmetric centers in a molecule. In general, the number of configurational isomers of a molecule can be determined by calculating 2n, where now equals the number of chiral centers in the molecule. This holds true except in cases where the molecule has mesoforms. Example, tartaric acid contains 2 asymmetric centers, but 2 of the isomers are equivalent and together are called a mesocompound. This configuration is not optically active, while the remaining 2 isomers are D and L mirror images, that is, enantiomers. The mesoform is a diastereomer of the other forms. The families of 4, 5 and 6 carbon carbohydrates contain many diastereomers because of the large numbers of asymmetric centers in these molecules. Applications: as stated, 2 diastereomers will not have identical chemical properties. This knowledge is harnessed in chiral synthesis to separate a mixture of enantiomers. This is the principle behind chiral resolution. After preparing the diastereomers, they are separated by chromatography or recrystallization. Note also the example of the stereochemistry of ketonization of enols and enolates. See also, Knar-Ingoldar Prelog priority rules for nomenclature. References